talking about. Okay, so this is, think about, this is the extra outer membrane of the bacterial cell, and this is the inner membrane of the bacterial cell, and this is the pump, and inside the pump there is a channel. Okay, there is a channel. So you see the channel, this is the channel, and this part is the cytoplasm, nothing else. So basically what happens is there is another channel by which the drug goes inside, that is called the drug uptake. That is the drug uptake mechanism. Even the drug uptake mechanism has a very complication now these days, because especially when you have some disease, the membrane behaves completely differently. So you have to also tackle how the drug can goes inside. That is another problem with the cancer drug. Okay, because most of the cancer drug are actually hydrophobic. And because in our body, it cannot really travel to that particular place because the blood is hydrophilic. So it can have a very high problem with the coagulations. So that's why they call it targeted drug delivery. And then there are some different something called drug delivery devices. Okay, so that it can go to a particular places. This is a different field of research. But anyway, but our research is not how it goes inside. Our research is how it stop coming from inside to outside. Okay, so this is the protein. There are several, most of the 4 or 5 kind of pumps are available right now. Some of the crystals are available, some of them are crystal not still available because it is very flexible. Okay, this is how the mechanism works. So this mechanism is more or less established how it works. So even without seeing this, I'm going to explain very. Okay, so if you remember this blue part, this is called the MEXB part, or in a AXB part, same thing. So this is basically this blue part has also trimer. Okay, it's a trimer protein. So what will happen is every time the protein has 3 configurations. It's like a 3 configurations. One is called open, loose, and tight. Okay, so once the drug comes from the inside, that is the open part. So it basically takes the drug and then it rotates. It's like a rotational mechanism. Once it rotates, then it attains different configurations. So open, okay, and then loose and tight. When it is tight, the drug cannot come inside, but what will happen, it basically pushes the drug, it will up. So this is how it goes from the very bottom to the up. So every level of the protein has these configurations: loose, open, and tight, and by which the drug basically goes like a 1 by 1, step by 1, step by 1 step. And there is a particular channel by which the drug goes. Okay, so our goal is to identify what is this channel, what is the structure of the channel, which residues are important for a particular channel, can we block the rotational mechanism? That is the whole idea. And that is all efflux inhibitor works. That is how all efflux inhibitor works. Okay, you have to stop the rotational mechanism by which the drug expels from the inside to outside. Okay, so these are some of those molecules that are kind of approved, and some of them we discovered from the different screening level that's still available. And remember that if you see, these are diverse set of compounds. It's not like a single, this is, you see, if you think about the channel is like just a pipe, it is not really that. Otherwise, this would not be useful compared to this one. Because this one is very tiny. In the biologic sense, it's like a lock and key mechanism, even though this is not really helpful. But think about the volume had to be adjusted. Otherwise, there will be enough space to rotate. Okay? Okay, so what happens is that means that these compounds will target at a different level, at a different places. Okay, so depending upon this compound, we will explore where we can attach and where the binding energy is maximum. If the binding energy is maximum, then the rotational barrier would be maximum. So our goal is to increase the rotational barrier so that for a limited amount of time, the drug actually cannot expel. So in order to understand the channel, so this is the blue part and this is the one of the monomer. Every protein has a trimer part. Okay, and this is one of the pocket that it was, the crystal was not there really. So we, during the molecular dynamics simulations like computer modeling, okay, just to introduce what is molecular dynamics simulation, is nothing but you basically solve the equation of motions, Newton's second law. In fact, it is more than that little bit. It's a Langevin equation, not really Newton equation, because Newton equation is not, there is no damping. So once we solve this equation, we get time dependent positions and momentum. And once we get time dependent position and momentum, then using classical mechanics and statistical mechanics, we should be able to calculate any property that you want. Okay. So by this compound, what we do, we try to explore the channel. Okay. So our goal here to using this compound to basically to map the potential of the channel. Once you understand the potential of the channel, I mean electrostatic map. Okay, so then what we are going to do, we are going to reverse design the compound so that the electrostatically the interaction can be maximized. That is actually one method to design a drug. This is called the pharmacophore or fragment-based drug design. Okay, so fragment-based drug design is like you understand where is the pocket, you identify what is the pocket, you check what is the electrostatic map, you identify the residue, and then based on the residue and the electrostatic map, the main pharmacophore is there, and then the outer part of the compounds, like of this fragment, will be designed in such a way that you maximize the electrostatic interactions or you increase the hydrogen bonds. That's how the fragment-based drug design works. Okay, this is the same idea. Okay, so then what we did, we basically modified this compound sequentially one by one to understand, to increase, to channel this whole channel, and then we identify that there are some pockets which have some flexibilities. So the protein is very smart. You see, at some point you see that this compound is very flexible. Okay, but the problem is what you do not know, that there is a cytoplasm. That is how the smart guy is. Both sides the membrane is there. So the membrane pressure is really high. I mean, if you see this membrane pressure is really high, the protein has a very limited amount of option to change its configuration. But the problem is the cytoplasm part. You have a lot of, if you remember this part is flexible. Even though this is a barrel protein, but this part is flexible. It is not bound by the membrane. Membrane is really tight. So what happens is, even if you think that I found a channel there or I found a pocket there, so I can design a molecule there so that it can tight there, but the protein immediately recognizes that this is the outer body, this is not, I am going to like it. So what will happen is, because this has an option to flexible its like a structure, so it immediately open it. Everyone understand what I am saying? Because this part is not easy to flexible, because this is tight by the membrane. But this part is in cytoplasm part, it's a liquid part. So protein has an option to adjust its configuration so that you think that I found a good inhibitor because it is bound there. But if you wait for a very long time, the protein will adjust its structure in such a way that it will just go. See, protein will always try to find out a minimum energy state, okay, by putting this more and more energy like this. So that is the most problematic part, okay. Okay, so then we calculated this energy, okay, all those energies. I'm not going to discuss all this energy because it's kind of hard to discuss. Anyway, so this is another barrier for this rotational energy case. So what I mean is here, this is called the dihedral rotations. For example, if everybody knows stereochemistry, like I think it was in those dihedral rotation, right? This energy barrier in a stereochemistry, right? In a BSc level. So what it does is, you see, so you put one configuration in the protein and it looks very good for some time. Then if you wait for a very long time, what will happen is this dihedral will change to another position. It flips. This is called the flipping of the configurations. Once it flips, then what will happen? It lost a lot of hydrogen bonds. Once it lost the hydrogen bond, then it is no longer tight there. Then it will just go up. So the protein is basically, it doesn't like it here. So wait for a little time. It basically it's waiting. Suddenly it opens its belly, and then it's loose. All hydrogen bond lost. Then it goes up. So that's why it is very hard to design an inhibitor when the configurations is not only in the membrane, but when the configurations are flexible in the cytoplasm. That is the problematic part. Okay. So this is another. I mean, this is the details. This is details. This is inside the protein. So what we did here, you see that we try to locate this detailed interaction with the different residues. So when you try to locate the different residues, mostly you should target about the polar residues, okay? Not like a lysine or something. Lysine is almost not lysine like all those aniline. Aniline is useless because it don't do anything. Mostly you should target who can form hydrogen bond, because hydrogen bond has an enormous significance in biology, okay? There are so many mechanisms just driven by hydrogen bond, okay? So that's why we locate where we can found as an aggregate most of the polar residue who can form hydrogen bond. And then what we're going to do is we are going to reverse design a molecule in such a way that it can form more hydrogen bond with the surrounding residues. So now what will happen? So what we did actually, even the protein flexes its muscle, there will be some other fragment which cannot form hydrogen bond at that particular moment, but when it flexes its kind of belly, then when it's open, then those guys which is not hydrogen bond at the right now, but they can form on the other part. So what will happen is you give you more options. When at a tight configurations, when they're completely good, they can also form hydrogen bond, but some parts are active. But when the protein try to open its belly, then what will happen? Those guys are like inactive. Now they will be active to form the hydrogen bond. But in order to do that, you have to find a sweet spot. Sweet spot in a sense, you have to know exactly when the protein opens its belly, which residues comes closer to the drug. You understand what I mean? Because you see, this is like a pipe. Now, in the inner surface of the pipe, there are some residues which are now open to the or making hydrogen bond with the drug in the initial configurations. But when the pipe, the radius is increasing, it's not just simply increasing, the protein will restructure itself. So certain residues will come now in the inner surface of the, in the outer surface of the inner membrane, or some residue will go inside. So there will be some restructure. But that is the trick that you have to do. So you have to maintain a situation in such a way that the overall hydrogen bond, even some residues will go inside and some residue will come outside, the overall hydrogen bond should be more or less preserved. So that's why the binding energy more or less should be same. So then the protein cannot expel. That is the trick that you have to use. Okay, so this is how the trimer, this is one of the pocket. So that pocket we found it, this is the pocket. So this is called the volumetric analysis, by which you can, so once you calculate the volume of the pocket, maximum volume of the pocket, and then you can go to the library. There are thousands of compounds, drug-like compounds, then you screen those compounds and you fit it there. And then you run for a very long simulation to understand what is happening, if the guy is really staying there for a very long time. Okay, this is called QM studies. Okay, I don't think, QM means this is more the classical, or some part is quantum calculation and some part is, the rest of the part is classical. The idea of this calculation is, it will give you better picture than classical. For example, when you do the classical simulations, the electrons are not really involved, okay? So the hydrogen bonds, really the hydrogen bond, the origin of the hydrogen bond is basically a fluctuation of the electrons, okay? So sometimes what happens is, if you do a quantum calculation, then what will happen, dynamically you changing the electrons. But in a classical simulation, you do not have that options. So you see better picture in a quantum calculation because this is a dynamics. The protein is doing the dynamics. So during the dynamics, you actually also see how the electron density is changing around the molecules. So if the electron densities or something, you can think about polarizations. Okay. So if this molecule, my drug molecule, is now polarizing more residues from this inside the protein, then it should form more hydrogen bonds. So that is actually better. And in order to do that, you have to do some quantum calculation to see really what is happening. Okay, so this one. Okay, so this one is another trick that we did. Okay, remember this the first structure. Now we are focusing on this one. So we focus this one, and this one. So look at this one. What is happening there? This guy is really smart. You see, there are 6, these are called coil, helix coil. Everyone knows helix, right? Helix? Okay. So if you see that these 3 helix and these guys are 3 helix. Okay. So this kind of red color and kind of cyan color. So that there are 6 helix. This is on the top of the, like a protein. This is the external channel of the protein. Okay, external channel. So these 6 helix actually, they forms a gate. There's like a gatekeeper residues. What happens is, once the molecule is there, this is experimentally actually observed. Once the molecule is inside of that channel, okay, it sends some electronic potential to the top of the membrane, and the membrane, on the top of the membrane, it changes its pH. Okay, once the pH changes, then the hydrogen bond situation actually changes, then this closed condition will go open. That is the last step of the expulsions. Okay, imagine that the drug is somewhere here. Okay, so once the molecule is here, the protein sends some signal. This is called the electronic potential signal. Okay, and then there is a arginine residues on here. There are some arginine residues here. It changes its pH. Once the arginine residue changes pH, it lost its hydrogen bond. Okay, once the hydrogen bonds are lost, then what will happen is, you see, this guy is now closed. That means the drug is actually still inside. Now what will happen? This guy will open. That is called the pore opening mechanism, and it is purely pH sensitive. Every time if you have a drug inside the molecule, once the molecule is inside, it sends a signal, change the pH, hydrogen bond lost, it opens. Drug goes out. Once the drug is not there, the pH will come back to the normal, again it will close. Okay, so that is how like it's like an enormous, it's like a cascade mechanism. Every time it goes like this. So what you can do here, can we change the pH in such a way that it will never open? Okay, this is for bacteria, this is not our body. If our body cell also has this kind of pump. They have a different things to expel. For example, there are different chemicals which is very bad for our body. In the middle of the night, they also go outside. But this is bacterial cells, so it's better to, whatever the toxin is, drug is, stay inside is good. Okay, so what you can do is, now they design an inhibitor in such a way that once the inhibitor is very close to that channel or just below this, it should not send the signal, so that the membrane, the top membrane should not change the pH. So basically you have to block or you have to cut out the signal network. Everybody understand what I mean? No? So once the drug is here, it sends the signal on the outer membrane. Okay, I am here, open the gate. And how it open the gate? It sends a signal, change the pH. Once the change the pH, lost hydrogen bond, it opens. These three helix opens. But now you can design an inhibitor, not drug, which will not send the electronic signal. That means the potential of the drug molecule and the potential of the inhibitor should be huge difference, so that the inhibitor will not affect the local environment, so the electrostatic difference or electrostatic potential difference is not that, or the barrier is so low, in a sense, the potential difference is so low that the outer membrane do not even recognize that somebody is there. So if somebody is not there, then it will not change its own local pH. Remember, this is local pH. So it will not change the local pH. If it is not changing the local pH, then it will always close. That is the target. So that is how you also can design an inhibitor, a tiny inhibitor, so that it will go there, but it should not disturb the electrostatic difference between the pore and the outer membrane. This is exactly how your potassium sodium channel works. Once the membrane, the ions are inside, it basically sends the potential difference, and then it opens the pH and it goes outside. The channel is not always open. If the channel is always open, then everybody will come and go. This is not going to work. Everybody has a gatekeeper residues, and all gatekeeper residues are pH sensitive. Once the calcium, potassium, all are inside, they basically creates a potential difference. Okay, and because of this potential difference, the local pH changes, those residues opens, and they'll go up or down, depends on the pH difference. Concentration difference, or concentration difference, in a sense you can think about potential and difference, electrostatic potential, because these are charged particles, same thing. Okay, there is a movie, I don't know where it is. Okay, so this is another interesting fact is that we found, this is actually exploited this to design inhibitor. Most of the cases, in this case, there is something called metastates. Okay, it's neither completely like a ground state or an excited state, something in between. Okay, most of our biological system, almost you can think about 90%. All enzymes are all who are kind of responsible for our body mechanism. Most of the cases they work from metastable state, because from the metastable state to the active state, the energy requirement is less. So it will not go to the complete low energy state. Otherwise, you need a huge amount of ATP. You know ATP, right? So you have to burn ATP to get the energies. So in this case, the system is basically in a metastable state, so that it needs a little amount of energy to do whatever it's supposed to do. Okay, so we found this metastable state, and what we did actually, we do not show here. So we explored that metastable state and we locked the metastable state. So what we did that, so it should not cross the metastable state. It should be always go back to the, so you find the inhibitor in such a way that it should not even close to metastable state. It should go to the ground state. So the rotational energy barrier is even more. So you put an inhibitor, the protein will change its structure no matter what. Once you put some foreign body, the protein will adjust its structure. But the orientation of the structure should be such that it go to the even lower energy state. So when it's try to open its pore, it needs more and more energy. So the more energy will not available to the bacteria. Okay, that is another goal. Okay, so this is how you close and open. These are energy barrier, how you can calculate that. And based on those energy barrier, you can design different molecules. Okay, so this is the pH. You see that at a different pH, this is called 4, 7.5. So at a higher level of 7.4, you have a different, and this is called, let's say 7.5, and this is 0.4. So at very acidic pH, this guy is closed. Okay, and when the pH is very close to 7.5 or something, little just go over base, okay, or 7.5, you see this is a maximum opening. So that gap you have to exploit. I think there is a movie. Where is the movie? No, the movie is not there. Okay, so how much time do you have? 20 minutes? Okay, 20 minutes. Okay, so another part, that is another problematic part, this is called cytotoxicity. Okay, what happens is, once you have a drug, then the drug can go inside for a drug, and then it will not go completely outside, but rather what will happen when the protein basically opens its belly, then it will go to the cytoplasm. So it is not coming to your like blood or something outside the membrane, but what will happen, it will just go to the cytoplasm of the bacteria. Is that clear now? Okay, go back again. Yes, here. So the drug will come here. Ideally, it should go all the way. But once the drug is here, this part will try to adjust. Because of this adjust, and if the drug is really small, and then what will happen? Protein will open some channel, then the drug will just go here. So it will neither go outside, neither stay inside. So in this case, it is very, very weird. It's very hard to stop it because now the barrier, you do not know when it will open. So you do not know where to stop because it can just send this anywhere. This is called egress pathway. Okay. Okay, so this is called the egress pathway. Okay, so for this kind of stuff, you have to have another set of inhibitors because this is not the real channel that you are trying to block. You have to block the egress pathway of the protein so that it should not also send to the cytoplasm. You see, you can target the top part. Okay, you can target the bottom part. Only bottom part is the best thing, but you cannot really do it. Okay, so but the problem is the middle part is the most problematic. Okay, the middle part, if you target the top part, but the drug can come inside and then it will go to the cytoplasm. Essentially, the drug concentration inside the cell is still less, so it is not going to work anyway. Okay, so you have to target also the egress pathways. So for in this particular case, you have a different kind of molecules that you can block those egress pathways. So only in a sense, only computer simulation will be able to do it to find this egress pathway. There is no so far experimental technique by which you can find the egress pathway. In an experiment, you can express the protein on the particular membrane and then you put it there. You can find out the drug is inside the cytoplasm or not, but you will never know how the drug basically travels from this protein to the cytoplasm. Only the protein simulations will tell you which basically the path or which helix is opening or which coil is basically opening. So in that case, computer simulation, you see these are the path that we discovered for this particular case. And sometimes this is also called allosteric site. So that is the combination therapy. Okay, that is the combination therapy that we used to do. So you block a main inhibitors, and then you also add some small molecule to block those pathways. So by this way, you put this concentration of the drug as much high in the bacterial cells. Okay, this is how we calculated all these things to get that part, but I just wanted to go. Okay, so this one is very nice statistical game, mathematical game. This is called the graph-based network calculation. So what it does actually, think about something like this. So I put a molecule here at the very bottom, okay, very bottom, because they are all the proteins are basically like think about like a primary structure, they are connected, okay. So this once they put with the molecule, the protein from the very top to bottom, they know that somebody is there, okay. Once the protein sends something, even if it is a very far, 10 angstrom, 20 angstrom, 30 angstrom, 40 angstrom far, the protein know that at the very end that somebody is there. The question is how they know. Experimentally, it has been found that there are some free electrons which travel from the very bottom to the top. For example, when you have a protein synthesis in ribosome or something, there are some signaling mechanism by which the ribosome knows exactly if the protein is really good or not. I mean, if the protein translocation is really good or not. If it is not, then there are some different enzyme, the protein will again break down and it will go back again to the original ribosome sequence so that it can have a new protein, the good protein. Same way, the mathematics, or this is called the network theory, we can calculate that once the drug is just induced in the protein on the channel, which path the protein is sending the signal. Okay, this is called the node-based signal. So even though, you see, even though the protein has only, let's say, but a single protein, you have only primary structure, right? Only one chain. But once it has a three-dimensional chain, you never know if it is only the same primary structure or if it is a node-based signaling. Because maybe because of this one, some residues are very close to some other residues, but there may be some coiling here. So there may be some shortest path by which it sends the signal. Everybody understand now? Think about something like this. Like you have a very big, like a thread. Think about this is a primary structures. When you put all this together in a very particular fashion, like a protein, then what will happen? Even some residues, like a residue number 1 and residue number 100. In a primary structure, there may be 1 and 100. But because of the three-dimensional structure, tertiary structure, they may be very close. Because of this close, maybe residue 1 sending signal to 100 that somebody is there, not like 1, 2, 3, 4, 5, 6, 7, 8, 9. So your goal is to find out that what is the shortest pathway that protein is sending signal that somebody is there. And if you can chop that signal, or if you can truncate that signal that somebody is there, so that you do not have a chance to change its own like reconfigurations. That is the advantage of this network analysis, and this is actually used for mostly drug design now these days. Okay, so by this way you can actually discover that which allosteric effect is controlling the whole mechanism. So if you know the allosteric, everybody knows cooperative effect, right? That's what you said, no, right? So the allosteric effect is kind of broader game of the cooperative effect. Most of them, they are very close to the main pocket, okay, but they can control the mechanism of the main pocket. So what you can do that, by doing this analysis, you can identify which allosteric pocket is playing the main game. So if you can block that allosteric pocket, then what will happen? You completely block the whole network process. And if you block the network process, then you find a good inhibitor, so that protein do not have a chance to change its orientations. That is the goal. Otherwise, what will happen? That the allosteric, even though you block the main pocket, but the allosteric pocket will send a signal and the protein will change its own configuration. Then there will be another channel by which the drug will just go outside. Okay, so this is how it is done. Okay, so this is the allosteric pocket that we found, and this is the main pocket. Okay, this is the main pocket, and this is the allosteric pocket we found. So similarly, we design different allosteric inhibitors, and this is really working. This is really working, and recently we just started one project with guest foundations on this antimicrobial projects, antimicrobial prediction for pneumonia. Okay, lastly, so this is kind of, everybody is doing, so we started 4 or 5 years ago. This is called this, how you can design a better inhibitors, or a dark, in this case we are not talking about which one are the good inhibitors. So machine learning, what happens is, it will save your time, huge time. Okay, it's like a mapping. In a simple sense, It's a mapping which is good for you based on certain features. So you put your features, make a mathematical model, which is actually called, in a real sense, it is also called features. This is called, there is something called feature matrix. Okay, and then you just put it into the 10,000, 20,000, 20,000. In fact, we screen more than 10 lakhs compounds. Okay, 10 lakh compounds, and from there you can select which are good for your particular protein and pocket, etc., etc. And based that, we basically found out those compounds are for good for this, and then we validated our model with respect to certain experimental data. Okay, and we found out, okay, so these are the validation for a machine learning model. I'm not going to go details because most of them we do not know. Those 6, 7 compounds, these are really good. Okay, really good in a sense, these are good for 2 pumps. Okay, and some of them bounce in the different places which has been discovered, not discovered yet. So we are going to test with some of those experimentalists group. That is what we are going to do with something called, there is a company in Bangalore called Syngene International. So we are going to have a collaboration with them to identify if this is really works for a Klebsiella pneumonia. Okay, so that is our kind of findings that are based on all mechanism. Once you know all mechanism, then you design a machine learning model, you screen the molecules, again you come back to your model, and then you validate with your experimental data. Once you are confident, then you give this molecule to the experimental, and they will express the proteins, and then they will say if it is really working or not. Now currently, so this is not beyond, this is beyond your research, that this is for you. Now there are different groups in the world. Now they are designing antibiotics. Some of them are in trial 1. Okay, trial 1 is relatively easy. Trial 2 is very problematic. Some of them are still in trial 1. They are designing antibiotics which itself acts as an inhibitor. So you do not really need a drug plus inhibitor. So the drug will itself as a works as a inhibitor. Only in that case you have to add little more drug. Not more, I mean not that much. You see, this is like a molecular level. When you have a 500, okay, you know, it's not really 500 because the API is relatively low. 500 mg, this amoxicillin is a huge number of molecules, right? Only few molecules will go to this pump and they will stick. So it's not really, you really need a lot of guys, but still, so far I saw this in the Bangalore conference, some of those Germany companies, they are showing, they found some antibiotic, but the dose are really high. The dose are really high in a sense. Right now, this is almost 10 times than what is applicable now. So that means it is not really a drug. I mean, if you add this drug right now in your body, you will die in a toxicity, drug toxicity. You see, drug is like a molecule. If you put more drugs in your body, that will be toxic. It's a chemical anyway. Okay, so drug is, it's a dose dependent. If you put a higher dose, you will die in the drug toxicity. So right now they are not very confident, but they are hoping that there are 4 or 5 drugs in the trial 1, so still they are good. Okay, and one of them is one of the Bangalore company. There is something called Bugworks. Okay, this is those guys are in the Dr. Reddy's, but those senior guys they retired, and then they open a company, and now they are showing some antibiotics. This is in trial 2. You see, trial 2 in India and trial 2 in America, they are completely different. Okay, so in FDA approval, trial 2, FDA trial 3, this is a huge task, and Indian data is not really, unfortunately, it's not very reliable. Okay, so still they have to go to the for European market or in a American market. So what they did, they really did something very weird. They went to Australia because Australia drug regulation is relatively, it's like almost India. So they get a license from the Australia, and now they tried to do trial 2. Okay, so there are some promising results, but they are not showing the bad results. I mean, there are some bad results they are not showing. They are showing the good results to get the money, but there are some good results. The drug itself as a inhibitor. So this is for the pneumonia because there is a huge funding by those US companies, that the pneumonia is now, all those drugs related to the pneumonia is now almost drug resistant. Almost all pneumonia antibiotics, especially in India, are almost to some extent drug resistant. That's why if you have a pneumonia, you have to go very quick to the hospital. If you wait for a very long time in a home, there is a high chance, if you have a pathogen which is drug resistant, then it can affect your heart and kidney within 7 days. Within 7 days. So if you have a pneumonia by suspect, you better go to the hospital. They have a different drug which is not available in the normal store. Okay, so these are something called colistin, etc., etc. So they have a completely different level of drug, which is very expensive, by the way. A single vial can cost you 50,000 rupees or something. So those are like this is only available in hospital. You cannot purchase it. You cannot purchase it. This is only available to them. So this is almost like when you are almost like a half dead. So that is why there. And then there are some trial 2.5, they call trial 2.5 drugs. This is for cancer. Actually, some of those drugs, actually India also developed a new antibiotic. I think I'm done with the time. So AstraZeneca also did it, and so this is a very promising result. This is the first Indian grown, Indian developed antibiotic, which is very good actually in a sense. Let's see, okay. But most of the drugs are in a very, very bad level. This is overuse of the antibiotics. Everybody is using antibiotics. Okay. Okay, so this is my group, and this is our, by the way, we are actually celebrating 100 years. So even though it was not 100 years IIT, this is the Indian School of Mines. Now it has converted to IIT Dhanbad. And this is the old, this is called the Heritage Building. This is the 100 years building. Okay, and this is my group. And some of the students are not there, they are already in US, they are doing some postdoc. So this is a little old pictures. And for this kind of calculation, you need really good computers. Not computer, they call HPC or call high performance computer. So for example, you need really like every day you need at least 6,000-7,000 like hours or something. So it's a very like a money affected. Now these days there is something called GPU. I don't know if you know. It's called graphical processing unit, which is very good, but it's not cheaper. By the way, it's very expensive. But it's in a limited space. You can do a lot of good calculations. Okay, and Indian government has done a very good job. They opened a policy. This is called National Supercomputing Mission. Different bacteria or not. So these are like blood, and then you can almost check it. So mostly this is hydrogen bonds game, okay? But the main game is the electrostatic potentials. That's how we change the pH.
I have one.
Yes, sir.
Can you tell me a single molecule that is developed using computers, machine learning?
Not for a drug right now, no, exactly not.
Not a single.
No,
Okay.
not which is in the market. Not in the market.
So what I learned from my research work, this resistance is very common.
It's very common, yes.
Very common. So many people use nanotechnology
Yes.
to overcome this resistance.
Some of them, yes.
Instead of your method.
This is one of them.
Which one is better and why?
You see, the problem is so big, everybody is trying to kind of attack this problem from a different perspective. Okay? Nanotechnology has its own problem. For example, it has an advantage, of course it has an advantage. The problem of some of the nanotechnology problem is you really do not know what will happen to those nanoparticles after injecting your bodies. Okay, some of the techniques, okay, but some of them are really good. For example, some cancer techniques, they're really good. Some of those nanotechnologies are really good. For example, if you have certain molecules inside these vehicles and you put it there, then you radiate it, and based on that, the drug will deliver to the particular specific particles, right? But the question is, for a long time, if a cancer patient is taking those molecules for a long time, you really know the kinetics, or this is called the pharmacokinetics of all those particles. At some point, those extra molecules that you are using as a delivery methods, it has to go through either your urine. Most of the cases, it goes through your urine. If it is not goes through your urine, either you die with your original disease, or you will die with your kidney problem. Okay, that is another problem with the most of the higher drug side effect, because once you put all those molecules, once they are done, the pharmacokinetics is not known. So I cannot say this method is really superior than other method, because everybody is trying to do one goal. Everybody has a goal, and they are trying to attack the problem from different purpose. This is known for a very long time, these efflux pumps. Because the mechanism is known, people are trying to use this knowledge to build up, can we build something new? Okay, that is the idea. For example, now there are some different pumps which is now available. Okay, so available. Crystal is not really there. once the crystal is there, I'm sure they will develop something very nice inhibitors. But those inhibitors so far, okay, they have also their side effect. But the problem is every molecule has the side effect. The problem is you're trying to, for example, if I have a disease, let's say I have a fever. For a certain case, I have a fever, right? So I have to judge if the side effect of the drug is more or the fever is more dangerous at that particular time. So it's kind of balance. Okay, that is how it is.
My last question. How do you measure the pH of the system? How reliable are your methods?
This is called the pKa method, called the constant pH molecular dynamics methods. This is very good. Almost you can call like a 5% here and there. Okay, 5%, more or less 5% there. Although there is a little caveat here. In this computer technique, it will calculate the pK of a residue, not a particular atom like a hydrogen atom for a particular. Imagine that, and in a chemistry point of view for a student, imagine that a particular molecule or a particular atom having a 3 hydrogens. So 3 hydrogens should have a different pKa at some point. But in this case, it is not like this. Okay, in this case, the pKa is designed for that particular atom of that carbon or nitrogen, or this most of the cases nitrogen or oxygen, because that is the hydrogen, they are kind of either go or they come. Okay, so the pK is not really a particular hydrogen like inorganic chemistry, that pK of this first hydrogen, second hydrogen, third hydrogen, not like this. Okay, so this is pretty reliable, because those like a high level calculation, and it takes 2 months to, this is called the pH titrations. I mean, here it is also called titrations. Okay, so but this is very good. This is based on Monte Carlo method, so it is very good.
All right, thank you very much.
Yeah.
Sir, what is the time span between the opening and closing of that OPRS channel?
It is almost in a microsecond. Sometimes some of them are microseconds, and some of them are in a nanoseconds. So it depends on the bacteria to bacteria, okay, and it depends also on your body to body. For example, imagine that you have a, this is called the pathogen grade. I don't know if you know or not. Imagine that I have a bacteria, and the bacteria can have a different strain. You know strain, what I mean? So the bacteria can have a different strain, right? So each strain can have a pump, and each pump can have a different this resistance. So it is not like that it's universal, but more or less the time frame is very quick. It's very quick, okay?
Thank you, sir.
But the problem is that bacteria is really smart. Okay, even in fact the bacteria will pretend that it's not there. You see, some of the virus and bacteria can stay in your brain for 20 years, and they can come back after 20 years, and you will not even realize that the guy is inside your brain for 20 years. Some of the bacteria can, actually there are some recent news that one HIV virus in America was found after 26 years from the brain of a kid. I mean, it's not a kid anymore, he's like a big guy, but it is there for 26 years, the virus was dormant. Okay, this is another mechanism by which now they are trying to kind of handle with it. Those bacteria will be extremely dangerous, because they actually, even though they are dormant, but they know your body very well. They almost, it's like an antigen, you know, like an antigen antibody. They are ready for anything. So they are ready for almost anything. That whatever the drug you use for your, from the very child to like up to this year, they are almost exposed with everything. And only thing, they are just silent there, and at some point there is some triggering point, they are active. And they started to amplify, replicate, and then once they come back, almost guarantee you will be dead. And that girl is dead actually.
I think
Okay, we can talk later maybe.
yeah, Ramesh, I think we can discuss it with sir during the lunch session, right? We are running a bit late. So once again, thank you, Dr. Patro, for your wonderful presentation. Our next speaker is Professor Dr. Joe Otsuki. He is the professor, College of Science and Technology, Nihon University, Tokyo. And before formally inviting him, I would request Professor Chittaranjan Sinha to formally.
And Professor Otsuki, you know, he did his doctorate degree in engineering in Tokyo University. And then he traveled to France for doing his postdoc with the Jean-Marie Lehn group. and now he is the head of the graduate school of Nihon University. There are 2 campuses. Now he is the just at the rank of the dean of this university, and he is traveling several times to this Kolkata, and during his traveling to Kolkata, I arranged his talks in different institutes. Even he visited last time in 2 schools in Medinipur. School, college, institutes, university, in many places. He is so liberal, and even he enjoyed the jhalmuri at Digha. So and his detailed biodata, you will go to the website and can get it. So it is not necessary to spend time by reading all these things, but his area of research, particularly in photochemistry, photobiology, spectroscopy and supramolecular chemistry. Professor Otsuki is also widely respected for his interdisciplinary research, scientific vision and commitment to international academic collaboration. Many of our Indian students did postdoc in his laboratory, and after he also, because of his contribution, scholastic contribution, Professor Otsuki has received the Research Award of the College of Science and Technology in Nihon University, and a special lecture by Young Generation Award, and the Chemical Society of Japan also awarded him, and also Indian Photobiology Society awarded him with Sir J.C. Bose Endowment Award in 2004, and Indian Chemical Society also awarded him. He is also a member of Indian Chemical Society and Indian Photobiology Society. So his title of the talk is Intermolecular Interactions in Molecule-Based Devices and Materials. So I do invite Professor Otsuki for his talk.
Can I have a microphone? Good morning or good afternoon, perhaps. I'm not sure. Good afternoon. Okay. Thank you very much for inviting me to give this nice opportunity to talk my works. And thank you very much for Professor Sinha-san. We put an when we call somebody, we put san after the name to express a kind of respect for him. So I often call Sinha, Professor Sinha-san. Okay. What I'm going to talk about is intermolecular interactions in molecule-based devices and materials. But I most exclusively talk about porphyrins I'm working with for some time. Before going into chemistry or science, I'd like to introduce my university a little bit. I'm working for Nihon University, which is a private university. Japan has national universities and private universities. And number of student-wise, private universities dominate, but research-wise, maybe national universities are more well-known. But I'm working at Nihon one of the private universities. One of the private universities, but it's a problem and has we have 16,000 students per year, and we have 16 colleges and schools, and we also have high schools, junior high schools, and elementary schools, all over Japan. But universities, we have some colleges in the college locations are local, which is these two are the College of Science and Technology campuses. One is in central Tokyo, and the other is in Chiba Prefecture, the next prefecture to Tokyo. And I'm working in Tokyo area. This is a new building, but my chemistry building is quite old and small. Okay, and because I'm in charge of graduate school of this college, and I like to advertise a little bit about our graduate school. And we have 16 majors, but basically any fields we cover. And I'm working in materials and applied chemistry here. And we have to pay at least. And if we have a large cavity here, we can selectively incorporate some guest molecules like this to develop into a host guest chemistry or molecular sensor, something like that. And this is one of the, and this molecule we have prepared, and we put a zinc ion here, and then two of these molecules assemble into a face-to-face dimer here. The crystal structure is like this one. And this is a crystal structure, and these two porphyrins are slightly twisted with each other, and so depending on the direction of the twisting, they are chiral, P and M, and in the crystal structure, P and M alternate like this. It's a beautiful structure, but the quality of the structure determination is low due to a large disorder and implicit solvents around here, but the overall structure is quite nice. And this is representation of P and M chiral structures using Japanese toys for kids. And we have substituted by pyridine by phenanthrolene, which is more rigid without rotation around the pyridine group here. And we diluted and diluted and diluted how these assembles are going back to here. And if we use a more rigid phenanthrolene here, it is more stable and to the lower concentration range. So the rigidity of the binding site is important to stabilize the dimer structures. But the intermolecular distance is 5.0 angstrom in the hope that there will be a cavity between these two porphyrin molecules. And here is the evidence for the formation of the dimer structure upon addition of zinc ion here. These ESI mass peaks are all of these corresponds to this chemical species, the difference being the number of counter anions. And similarly, for the diacetylene spacer case, we have these peaks corresponding to this structure minus the number of counter anion. So this can be formed, and proton NMR. Here's the proton NMR of this molecule, and we put zinc ion here. The proton NMR shifts greatly. Some of the peaks going upwards, and some of the peaks going downward. And so, how do we know the structure in solution? If we get crystal structure, the solution is known. But if not, or how do we know that the structure in solution is similar or the same as in the crystal structure? That's a very challenging question to solve. And but in this case, these are almost all aromatic. This molecule consists of aromatic components. Aromatic components have a ring current effect on other protons in NMR spectroscopy. And this is a very classical method of predicting the chemical shift changes of these protons. What we do is we put equivalent magnetic dipole moments on each one of the aromatic rings. And so we can calculate the effect of these aromatic rings on a particular proton. And we have make a model. Oops. Model we don't have. I don't. Oops, sorry. Yeah, make a model like this. And we have some separations, we have some rotations, we have some rotation around a single bond here, and we can make some molecular models. And if once we get a model, we can calculate the effect of these aromatic rings to particular protons. But how do we know? How do we know these parameters, the distances, angles, etc.? So that was a problem. Normally, first thing we think about is the least squares fitting. We can change the angles and distances and to minimize the difference between the calculated and observed chemical shift changes. But in this case, how do we know? The first thing is how should initial values be chosen, and strong correlations may exist. If theta 1 is some values, theta 2 can be different values. Theta 1 is different values, theta 2 can be different, similarly explaining the model. So I used a Markov chain Monte Carlo method, which is like we have treated as a kind of vectors, and so this is a high dimensional vector, and we change these values a little randomly. It's the origin of the name Monte Carlo, and we have prepared some walkers around here, and on a high dimensional parameter space, and then let them to walk around, and each point they calculate the how the value of these parameters are good to reproduce the experimental results. And then we have prepared tens of walkers and let them walk around 100,000 steps, and then explore the likelihood for these high dimensional parameter space. So basically, that's the Monte Carlo Markov chain method, and the result is like this. And so we have explored a very large parameter space simultaneously and obtained these results. This is a projection of high dimensional distribution to each one of the parameters, and from these, basically these parameters can be behaved very well. Some of the parameters bad, so we have large uncertainties about distance between these two porphyrins, but we can analyze this way very complex systems using MCMC, Monte Carlo Markov chain method. And then this is a predicted predicted chemical shift positions, and this is the experimental results, and agreement is reasonably good, and this is the most likely structure of the dimer. And these are some variations. We can obtain the best fit model, as well as how deviations can be possible from that model in a quantitative sense. So basically, there are some uncertainties, of course, but basically the dimer structures like this is very likely. So another thing is that how this is a very complex process. 2 porphyrin molecules and 4 ions assemble into one structure, and how do we analyze it? Basically, we do titration to the porphyrin solution. We add zinc ions incrementally and recorded a absorption spectrum, and some of them have shown very nice isospecific points, and some are not. This one, initially, the Sore band shifted lower energy side, and then changed the direction to up higher energy side like this. How do we analyze this? And this is another mathematical method for the analysis, and which is called multivariate curve resolution alternating least squares method. And the experimental results is just these titration curves is just a matrix of spectrums arranged in different additive concentrations, and then this matrix can be decomposed into a fraction of component changes versus the spectrum of each component. So these smaller matrix have all the information of this complex large matrix in principle, plus some errors. And to minimize these errors, we can obtain these component spectrum and how these components evolves. And these are component spectra, and this is how each component evolves. So there is some intermediate structure appearing and then decreasing afterwards. So in this intermediate structure, we assume that this is a lower energy absorbing species, we speculate this as these intermediate structure like porphyrins arranged more or less in a side-by-side fashion. So the complex could be very complex. We start from the porphyrin and we end up with a face-to-face dimer. Dimer structures like this. And the ions can added one by one, and in each time we can have this J-type side-by-side structure or cofacial structures like this. And we can experimentally distinguish these monomer type structures and side-by-side structures and face-to-face structures by spectroscopy, but we cannot distinguish between these two. But another absorption area we can distinguish by pyridine group and coordinated by pyridine group. And so combining these spectroscopic information, we also did, so in each step, there's one binding constant. So if we consider these all steps, we have 1 to 12 binding constants and very complex simultaneous equation systems. And so we have used the Monte Carlo Markov chain analysis again. And these are the projections. This is horrible. I mean, the binding constant cannot be determined at all for some binding constants. For some, there is a certain intermediate species is built up somewhat, but most of them are not. And so we can remove the insignificant intermediate species from the analysis, and then so only species building up somewhat is like this one, and these are not appearing in the whole titration process, and so we can remove those one and reanalyze again. Now we have a very nice sharp distributions for each binding analysis, so that we can say that these processes are how the complex supramolecular species are being built up. Okay, thank you. And this is for another one, and we can analyze all of these. And this is a summary, and Okay, I can use my own hand. Okay. What was interesting is that okay, thank you. Just press. Okay. The one without spacer have a very small number of intermediates, and one with a settlement spacer have 2 intermediate species, and one with the longest spacer have many intermediate species. So this is interesting because more longer spacer case have has a kind of more freedom to accept various types of intermediate, more freedom to move or conformationally flexible. So these things, these properties emerge from the analysis. And so once we can get the space. Once we get a face-to-face dimer, cofacial dimer with a cavity here, we can examine the host-guest selectivity, and for the diacetylene spacer, we can put this molecule as a guest. It strongly binds this one, and we have done all the possible reference experiments. This one, that's same guest with simple porphyrin, has a very low binding constants, and if we have even if we have a dimer, the smaller cavity dimer have a low binding constants. If we have the same molecule but without a dimer formation, the binding is small. Even this dimer, without nitrogen here, the binding is small, and this one without zinc ion, binding is small. Only with the combination of the dimer formation with a longer spacer group plus the phosphopyridine case, in this case, very strong binding is observed, which is evidence, we believe, of the incorporation of these types of structure. For the smaller one, we have pi-pi stacking interactions like this. And another one of the how we assemble molecular assembly is to use dynamic covalent bonds. This is a classical bond which you learn in organic chemistry course. This is an aldehyde and amine through an intermediate to form an imine bond. This is a reversible structure, and in organic chemistry textbooks, there is a pH-dependent reaction rates we learn. And this reversible reactions is useful because they automatically search for the most stable state thermodynamically. So this is recent review by Sebastian Ulrich in France using this strategy. And what we did was to use these aminoporphines with a simple diformyl pyridine group here. And these two assemble into these types of a cage structure. And we have collected precipitate after the reaction. We only get this nice mass spectrum. And if you did the same reaction in the presence of fluorine C60, we have only observed this mass spec without any trace of signal around here. So the difference between these two is 720, which corresponds to one C60 molecule. So that suggests the incorporation of fluorine inside. And luckily, we got the crystal structure, and I think it rotates. Yeah, this is the crystal structure we got. So the fluorine is incorporated into the cavity. And here's the crystal structure. The interesting thing is that here's a porphyrin, and porphyrin fluorine intermolecular distance is 2.77 angstrom, which is quite narrow than typical pi-pi stacking distances, which are around 3.3 to 3.6 angstroms. And more small details, what was interesting was that the fluorine's orientation, there are two fluorine orientations. This is measured at 93K, but there is two different orientations of fluorine's group we can distinguish. Here's the absorption spectrum and the fluorescence spectrum. Absorption, there is a slight solid band red shift by fluorine incorporation, which suggests some electronic interactions between the porphyrin group and fluorine group in the ground state. And in fluorescence of porphyrin is largely quenched, which suggests efficient electron transfer from porphyrin group to fluorine. These are porphyrin assemblies we have worked on for some time before, and the conclusion is that we have used the coordination interactions, and we have a little bit mentioned about dynamic covalent bonds as a strategies to assemble porphyrins, and we have the assembly have properties not observed in individual molecules, which are like energy and electron transfer among porphyrins, which was photosynthetic models. And by changing spacers, designing spacers, we have developed into host gas chemistry. And elucidating structures in solution is a challenging task, but a Monte Carlo Markov chain-based strategy can be effective. And elucidating assembly processes is also, MCMC is a powerful method. And dynamic covalent bonds, we have shown fluorine recognition. So these porphyrin assemblies are, the structures of these assemblies is regulated, controlled at the molecular level. So it could be some photo and electroactive molecular devices and materials for the next generation. That's what I hope for and looking for. Thank you very much. Thank you very much. I forgot to mention my acknowledgements. This work was partially supported by Kakenhi and Dhanyavad for your kind attention.
Thank you, sir, and dhanyavad to you. And I think we have some time for 1 to 2 questions from the audience.
Hello, it was a nice talk. So I have a question, like you have used the zinc as a metal center. So zinc is a redox inactive material. So I saw that your cyclic voltammetry have some oxidation peak and reduction peak. So is it based on zinc or some linkers are presenting or doing something?
The cyclic voltammetry I showed is basically pi, due to pi systems, not metal centered.
Completely linkers.
Completely
Ligands.
porphyrin core.
Porphyrins. So it is oxygen environment, oxygen or degassed totally.
In that sense, ligand.
Oh, in that.
Porphyrin. Yeah.
So another
Yeah.
question.
For the catalyst applications, we have to put catalytically active, redox active metals inside. Our team is working on some aspect of that, but I don't have any concrete results that can be presented to you. But we are very interested in redox active metal centers also. Good thing about zinc or D10 metal is that we can analyze NMRs in detail. Yeah.
These electron transfer that are occurring, can you detect like a real time, like a online system, like a in situ FTIR or in situ NMRs? Can you detect this electron transfer process? Like you are using any LED or external light sources, during this process the electron transfer occur. Can you detect this by any online system? What is going on in real times?
Real times, yes, it's a very fast femtoseconds, nanoseconds time scale, and so we use the transient absorption spectroscopy.
But it is ex situ, right? You take and then do this ex situ technique. Is it in situ that occurring like?
Yeah, it's in situ.
Okay.
In that sense, I think.
Okay.
Yeah.
Okay. Thanks.
It's excited by a femtosecond. So sorry, I can't hear.
Can you hear? Yeah. So, why exactly zinc porphyrin is used for this process, or any other metal with +2 oxidation state can be used for this porphyrin?
So your question is, why do I use zinc?
Yes.
Yeah, this is D10 metal, which has no unpaired electrons, and so it doesn't interfere with NMR measurements, and so it's good for the analysis in structure solutions. And also zinc accept one axial coordinate ligand, and so it can be used as a self-assembly to organize porphyrins into some higher architectures.
Okay, I think I have to stop here. And thank you once again, Professor Otsuki, for accepting our invitations and coming here and interacting with our audience and students. Thank you very much, sir. And before proceeding to our next session, I would like to add that during the inaugural session, one of our speakers, Dr. Bishwadip Banerjee from the IICB Kolkata, could not join us due to some prior appointment, but now he is here, and we will now officially felicitate him. And for this, I request Dr. Taposh Ghosh, who is the head of the Department of Chemistry of this college and also the convener of this seminar, to please come to the dais. And also, Dr. Banerjee, please come to the dais. Volunteers. So thank you, Dr. Banerjee. So he will be our third speaker, but this will take place after lunch. So we will all take a break for the lunch session. And I must add that the lunch session and the poster session will go side by side. So I think it will be a bit difficult, but we can manage, right? Because we don't have much time. So our distinguished speakers will be accompanied by Dr. Taposh Ghosh to the IQAC room for lunch, and all the other members of the audience, I request you to please go to the rooftop. There will be a lunch session for you, and we will return here around 2:30. So our next session will start at 2:30. So please be there. And also, I request all the participants to just remain with the WhatsApp group which has been created for this particular seminar for a few more days, because the e-abstracts will be shared in that group only. So please don't just get away from this group, and another 3-4 days, please be attached with this group. Okay.